So what would term number 10 be? What is term number 10 in this sequence? 34. Very good. So 13 plus 21 is 34. So we could go on and on and on forevermore. Now, last time we wrote a definition, a recursive definition of the Fibonacci sequence. So in this definition, we say Fibonacci 1 is 0, Fibonacci 2 is 1. So remember that this is the term number. So the term number 1 is 0. So on the right here is the value of that term. So term number 1 is 0. Term number 2 is 1. Huh? The term is this value here. Right. Term 1 is 0, term 2 is 1.
ไม่ได้แปลว่าภาคการศึกษาแปลว่าอะไรก็คือเทอมคือเป็น semester เทอม semester อ่ะก็คือ semester
โอเค
เทอมก็คือตัวแรกถ้าตัวเลข1คือ0ตัวเลข2คือ1อะไรนี้ไม่ได้แปลว่าภาคการศึกษา
We understand? Yep. So, term number n, for any value of n greater than 2, oh, I can't write.
If you move the paper a bit to the right. So if it goes this direction, so that's fine. So go to your left. So it will not block you.
So the term number n is term n minus 1 plus term n minus 2. So the previous two terms added together. So for example, if we try to calculate Fibonacci 5, so the fifth term, using this definition, Fibonacci 5, so then we apply our definition. It's not 1, it's not 2, n is bigger than 2, so we apply this line here, right? So Fibonacci 5, according to this definition, is Fibonacci 4 plus 3. That's right. Fibonacci 3. So we don't know those values yet, but we know that Fibonacci 5, the fifth term, term number 5, is term number 4 plus term number 3. So recursion means we solve the problem again. So now we have to find these two terms. So Fibonacci 4, which line of the definition applies? Is it this one? No. Is it this one? No. Is it this one? Yes, because n is still greater than 2. N is 4, so it's greater than 2. So what would this be? This would be Fibonacci 3 plus Fibonacci 2, right? Okay, so let's finish this one first. So by the definition, how would I calculate Fibonacci 3? What is that? Again, is it this line? N is 3, so it's not this one. So Fibonacci 3 is Fibonacci 2 plus Fibonacci 1. Okay, so according to our definition, what is the value of Fibonacci 2? We know Fibonacci 2 is equal to 1, right? We know that's 1. What about Fibonacci 1? Fibonacci 1 is 0. That's right. So 1 plus 0 is 1. So therefore Fibonacci 3 has the value 1. Right? So this value is 1. Fibonacci 2 is 1. 1 plus 1 is 2. So Fibonacci 4 is 2. Right? So Fibonacci 4 is 2. Fibonacci 3 is 1. 2 plus 1 is 3. Very good. So it says that the term number 5 is 3 by this definition. And is that correct? Term number 5 is 3. So we were right. Now, last time I gave you some homework. Do you remember? Do you remember the homework that I gave you? No? Anyone? This was the homework. Do you remember? Last time I gave you homework. Has anybody done the homework? You have a solution for me. Is that no? Okay.
ทำมาบ้างครับพี่ใครทำมาแบบนั้นบ้าง
No? All right. Well, the homework question said, write the Fibonacci function in pseudocode. Okay? Write the Fibonacci function in pseudocode. So I will show you how we could do that. So we want to write a function called Fibonacci, and the parameter to that function is the number of the term. So we could try to calculate term number 5 or term number 10, any term. And on the left is the value of the nth term. The value of the nth term. So, for example, if I were to say print Fibonacci 3, what would happen? 3 would be the value of the argument. That's n in this case. What value, though, would be printed? Print Fibonacci 3. So the value of 3 is given as input into the function, and the value of the term is returned, calculated and given back. So in this case, we print the result of Fibonacci 3. So 3 is given to the function. What value is returned from that function in this case? But what value would you expect to be printed? What value would be printed in this case? So 3 is the number of the term, So term number 3, and the value to be printed would be 1. Right? Term number 3 is 1. What about if I were to say print Fibonacci 9? What value would be printed in that case? Anyone? 21. Very good. So term number 9 is 21. So that value would be printed. So we want to be able to write in pseudocode this Fibonacci function. It should take the value of n as an argument, and it should return the value of the nth term. When we are writing a function, a recursive function in pseudocode, we have to write it based on our definition that we've created. So you remember this definition. So the pseudocode will be very similar to this definition. Oh, one other question. These two cases here, with n equal to 1 and 2, are called the base cases. So we know the answer in those two cases. If 1 is the argument, we know the answer is 0. We do not need to calculate anything. If 2 is the argument, we know the answer is 1. Do you mind just asking to use the phone? Right, talk. Second. All right, so when we write the pseudocode for this function, the first thing we have to do is we have to write our base cases. So in pseudocode, we would say if n equals 1, then what value is returned? What do we do? What is the answer if n is equal to 1? What is the answer? If n is equal to 1, the answer is 0. So therefore we return 0. Right? That is the answer that we calculate. if n equals 2, which is our other base case, then what do we return? If n is equal to 2, the answer is 1. That's right. So we return 1. It's the second case. Else, then the question is, what do we return? Can you work out the answer? So take a look at the definition, and that really is the answer. That is the answer. So if it's 1, we return 0. If it's 2, we return 1. If we come here, n must be bigger than 2. Maybe 3, maybe 4, 5, but bigger than 2. So we return Fibonacci what? N minus 1 plus Fibonacci n minus 2. That's right. And that's it. That's the whole function. So these calls here are recursive function calls. So, in other words, the function calls itself. Function calls itself. So when you learn to program in C++ or in Java or other languages, you can write this code in that language very, very easily. So anyone have any questions? Any questions? No? Any questions? No? So that's easy, right? Very easy. All right. Good. Good. Actually, recursion is a very difficult idea. It's a very difficult topic. But it's very good. Very interesting. Okay. So no questions. Right, I'll give you a minute to finish writing, and then we do another topic. You understand this? Yeah. You understand? Good. All right. Okay. So next topic. The next topic is called stacks. Stacks. And a stack is an example of a data structure. So you are studying data structures. So a stack is an example of a data structure. And we can think of a data structure as a way to store data.
Where is the data?
Now, the word stack is a common English word. What does stack mean in English? Do you know? Do you know that word? No? Stack. Stack. Okay, so these are pieces of paper, right? A stack means that we take one piece of paper and then we put another on the top, and another on the top, and another on the top. This then is a stack of paper. It is a stack of paper. All right? You understand?
Yeah.
So a stack means that we put one thing on top of another. So that this is a stack. Okay? So in English, we use the word stack very common. It's a common word. So we could say, for example, stack of books. Okay? Stack of books means that we have one book, and then we have another book, and another book, another book. This is a stack of books. Do you understand?
Yeah.
Yep. Now, one thing about a stack, if we have a stack of books, so I take one book, I place it down. I put another book on the top, and another book on the top. Which book can we access? What do you think? If I've got books 1, 2, 3, and 4. So if I have a stack of 4 books, which book can I access? Which book can I take away? Which one? Only one of them. Which one? Did someone say 4? Yep, the top one, right? I agree. If I have a stack of 4 books, I can only take the book at the top. If I take the book at the bottom, the whole stack falls down. I can't do that. Right? So, which book can we access? The answer is book number 4. And importantly, book number 4 is the book at the top of the stack. It's the book at the top of the stack. That is the only one that I can access. Nothing else. Okay, any questions so far? No? Okay. So, a stack is very simple, actually. It's very easy.
Simple.
Very simple. Right. We have only 3 operations for a stack. So we can only do 3 things with a stack. Nothing else. The names of the 3 operations are push, pop, and top. 3 operations.
May I go?
Sure. Push, pop, and top. That's all. So these are important names. These are names that you have to know. What does the word push mean in English? What does push mean? Yeah, right. So push means to do this, to push something away, right? So, with a stack, what push means is to add a value to the top of the stack. So push means to add a value to the stack. So just like creating a stack of books, we place one book on top of another, that is pushing a value onto the stack. The word pop What does the word pop mean in English? Pop means to explode, right? So pop in this case means to take a value off of the stack. So pop is the reverse of push. We push values on, but we pop values off of the stack. And the only other one is top. This means to access the top value in stack. Access the top value in the stack. So there are only 3 operations. It is very simple. Very, very simple. So let's take a simple example of using the stack. Any questions so far? Do you understand push, pop, and top? All you have to understand, 3 things. So let's take this example. Let's suppose the input that we have is A, B, and C. So A is first, B is second, C is third. That is the input. Now, I am going to write something in pseudocode. Okay? I will write it in pseudocode. And then I'm going to ask you a question. So you write this down first. So read X while have input push X read X, then while stack not empty print top and pop. So I want you to take a minute to write down that pseudocode, and then we will discuss what the pseudocode does. You take a minute to write it down. Can you read my writing? What is this word here? Empty. Do you know what empty means? Empty means blank. That's right. Nothing in there. No values. Right. Good. Okay, so you write that down, and then I will give you a question about it. Okay? Okay, so we have a stack, and we have input A, B, and C. Okay, this is a very simple question. Okay, you tell me, what does this pseudocode do? Can we try to follow it through? So first, I read a value. So the first value I read is A, just A first, one character. So I read A. Okay, you've got to tell me what happens. Do we have input? Yes, we've just read A. So I have a variable in my program called X. X is a variable. So the first time I read the value A. So the variable X at the moment has the value A. Okay? All right, then what happens? We have input, so I push. So how do I draw that? I push whatever the value of X is. X is A at the moment. X has the value A. So if I push X, what happens to my stack? What value is pushed onto the stack? Push X, the value of X is A. Right? So A gets pushed onto the stack. First value. Alright? Then I read X again.
B.
Right, so now I read B, so the variable now is B. It's no longer A. Right? So I go around the loop again. Then I push X. What value gets pushed? What does my stack? What happens to my stack? You see that the next value pushed on is B. So I've got two values. I'm forming my stack. Then I read X one more time. So I read C. And I push X, so the value C gets pushed onto the stack. But then there is no more input. So our input is finished. So then we come to the second loop. Now, can you tell me what that second loop does? What does it do, do you think? What values get displayed and in what order? So, is the stack empty? Yes or no? The stack is not empty yet. The stack has got three values. So print the value at the top. So what value gets displayed first? This is now the output. So what value gets printed first?
C.
C, correct. Because that's the value at the top of the stack. Then we pop. Yeah, okay, so pop, what it does, pop eliminates the top value of the stack. See that? Pop removes a value. So pop removes the value at the top of the stack. So C now is gone. Is the stack empty? Yes or no? Stack is not empty. Stack has got two values. Print the value at the top. What value gets printed next?
B.
B. That's right. Then we pop again, so B gets removed. Is the stack empty? No. What value gets printed? A. And then we pop again, so A gets removed. Now is the stack empty?
Yes.
Yes. So we stop. So what's happened? The input was A, B, C, but the output is C, B, A. So this has reversed the input. It has reversed the input. Do you know the word reversed? Reversed means to go backwards. So reversed means to go backwards. Okay? So reversing input, if the input is A, B, C, the reverse is C, B, A. So a stack is a very simple way of reversing input. Any questions about that? Okay, I don't have very much time, but I want to show you this. So this, you can take my notes afterwards if you like. But what I've drawn here can you just give me 10 minutes, right? 10 minutes, okay? Thank you. Okay, what I've drawn here is what we would call a maze. I don't know whether you know the word maze, but the idea is 0 is open, or O is open, and 1 is not 1, X is closed. So that means if I'm walking, I can walk along the O's, but I cannot walk over an X. You understand?
Yes.
So as children we play this game, right? This is called a maze. So my goal is to enter, to go in here, and I have to find a way through the maze so I can exit here. You understand?
Yes.
So what could we do in this case? We could walk in here. Then what would we do? Can we see a way through? I've forgotten actually. What is the way through? All right, so I could go here, 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 and then all the way down. Right, that would be a solution. So I would like to be able to write a computer program to solve that problem. All right, I would like to be able to write a computer program to solve a maze problem. So I could give that program any maze, anything, and it would work. It would find a solution to the problem. A stack is very good for this type of problem. So we solve this problem by using a stack. Okay, now the only thing I will say is when we solve it, we need a strategy or a method. And when I come into the maze, what do you try to do first? You could go down this way. We could try that, see if it works. So if we go down, we would go here, then here, then here, but then we're stuck. We can't go anywhere else. So what do you do then when you get here? You go backwards. So go here. Can we go anywhere else? Stuck again, right? So you go back again to here. Then we might try to go to the right. Right? So we need a strategy. We have to decide, do we go down first? Do we go to the right? Do we go to the left? Or do we go up? Okay? So I'm going to say that my strategy is to go down first. If we can't go down, we will try going to the left. If we can't go to the left, we'll try going up. And if we can't go up, we'll try going to the right. Okay? Now, I'm almost running out of time, but let me just show you the idea. So, we use a stack, and let's say we have coordinates here. All right, so we enter this maze, and we enter at position 1, 1. Okay? All right? So location 1, 1. Then, according to our algorithm, our strategy, we try going down. Can we go down? Yes. So we place that value onto the stack, so it'll be 2, 1. All right? Can we go down again? Yes. So that will be 3, 1. Good. Can we go down again? Yes. 4, 1. But now we're stuck. We can't go any further. So can we go to the left? No. Can we go up? No. We just came from there. Can we go to the right? No. Okay, so what do we do in that case for our stack? What do we do? Someone said we go backwards. What does that mean for the stack? What operation do we use? Push puts the values on. What takes the value off? Pop. So we pop top value from the stack. So now we're at 3, 1. So can we go down? No, we've already tried that. Can we go to the left? No. Can we go up? No. Can we go to the right? No. So we pop that one. So now we're back at 2, 1. So now, can we go down? No, we've already tried. Can we go to the left? No. Can we go up? No. Can we go to the right? Yes. So now we put 2, 2 on the stack. So if you follow that, I haven't got any more time, but you can follow that through all the way to the end. And what will you have on the stack? You'll have the path, the places that take you from the beginning to the end. Okay? All right, sorry, I'm out of time, but thank you very much for your attention, and I'm sorry that we have to finish the class now. All right, so thank you very much.
Thank you, teacher.
You're welcome. Thank you very much.
Bye.